All right, so we're going to talk about kernel machines for a little bit, and this will conclude our discussion of kernel machines and get us through support vector machines with the RBF kernel. Okay. So previously, in the two previous videos, we talked about high-dimensional embeddings and how that can give us nonlinear, turn linear methods into nonlinear methods. The next discussion was about how using high-dimensional embeddings, we can think equivalently about using kernels. There's a kernel form for a wide variety of learning algorithms. There's a kernel form for a wide variety of learning algorithms if you use a high-dimensional embedding, and in that case, you only have to have access to the inner product in the embedding space. And so you can sort of bypass the construction of the embedding altogether by just looking in closed form at what this kernel is. And now we're going to sort of turn that narrative on its head. We're going to start with a kernel and talk about the more general characteristics of kernels that we require to have it so that there exists such an embedding. But remember, in the algorithm, we never actually require the construction of the embedding, and so if we have some closed form for a kernel, that's all we need. Okay, so a Mercer kernel, K, is just a function that maps RP to RP to RP times RP to R plus. So this just takes in two of the inputs in the input space and then spits out some notion of similarity. That's how you should think about these kernels, as some notion of similarity, right? So it could be the number of words that two documents have in common. That could be a notion of similarity. Now, the only requirement is that it's a positive semi-definite function. And what does that mean? Well, that means for no matter what your data is, if you form the kernel matrix, which is just the kernel evaluated at xi and xj in the ijth position, so remember we formed this capital K kernel matrix, if that is positive semi-definite, then this function is positive semi-definite. So that's all we require, and that's what a Mercer kernel is, and that's our only requirement on the kernels in kernel machines. Okay. So we have a theorem that says that every Mercer kernel has a high-dimensional embedding, phi, which maps RP into L2, such that this K times x and x prime, K of x and x prime, is equal to the inner product in this space. Now, one caveat, one slight detail, is that this little L2, this could be infinitely long vectors. This is a space where the vectors don't necessarily terminate, but could be infinitely long. So that's the one minor caveat. So this high-dimensional embedding could be infinite dimensional. Now, it could include finite dimensional embeddings, like the polynomial embeddings, and all we would have to do is just say that all of the components after the dth component of the output are just 0. Right? And then it would be a finite dimensional embedding, and that would be fine. You can actually prove this using a spectral decomposition of the kernel function. So you have eigenfunctions and eigenvectors. You can prove it using that, in fact. So this is what this theorem says: is that there's actually a way of going in reverse. If you start with a notion of similarity between two data points, then you just have to check if that's a Mercer kernel, if that notion of similarity is a Mercer kernel, and then you have this theorem, which says that there's actually such a high-dimensional embedding. And all of our math that we had previously goes through in this case. So, that's the infinite dimensional stuff. That's a little bit of details that might be sort of pushing the boundaries of what we're willing to do mathematically in this course, but I think it's very interesting, especially because sometimes this high-dimensional embedding is infinite dimensional, right? It fills out all the components of little L2 of this infinitely long vector sequence. But again, we never have to construct this in the algorithm. We just have to be able to evaluate this kernel for all pairs of data points, form this capital K kernel matrix, and that's all we used. except when we go to predict. But when we go to predict, we just need to evaluate the kernel between a point and test points. So let's talk about one of the most popular kernels out there, which is the radial basis function kernel, RBF kernel. And that's this k of x and x prime, which is just equal to, this is, it's equal to the exponential of minus the 2 norm between x and x prime squared divided by sigma squared. So the sigma squared is called the sigma is called a bandwidth parameter. Sometimes it's written as gamma. And the basic idea is that, 2 points are similar if they're close in Euclidean distance. But how similar is determined by this thing, which looks like an activation function. It says x minus x prime, the Euclidean distance squared, you divide it out by sigma squared. So the sigma is like a unit of measure, right? So how many of these sigma units are the 2 points distant from one another? So if that unit is very large, then these points have to be very close to one another in Euclidean distance for this kernel to be small. Or sorry, have to be very far from one another for this kernel to be small. And then the high-dimensional embedding in 1D is, it turns out, so if we just think about x as being a one-dimensional point, so instead of Euclidean distance, we just have the square difference. Turns out that the high-dimensional embedding that corresponds to this kernel is equal to the following. It's actually an infinite sequence, so it's an infinitely long vector, and it takes the following form, where you have this e to the minus x squared over 2 sigma squared times this series. Okay. One correction that I'd like to make is that the gamma parameter, when we're using it in scikit-learn, is 1 over the sigma squared. And so the sigma is sort of the radius at which that we talk about as 1 unit of measure. So if that sigma is very large, then this kernel is going to consider more distant points as being similar to one another. And the gamma is reciprocal to that. And so if gamma is very small, then distant points are more similar. Okay, so let's construct a data set, just a toy data set to illustrate our purposes. We're just using just creating a uniform data set, and then we are applying just some arbitrary transformation to the data to get it to be univariate, just a single number, and then we're asking whether this arbitrary transformation is greater than 0 or not, and that's going to determine which class you're more likely to be in for a binary classification problem. So let's just visualize it. So this, it's like there's a latent variable, which is whether you're more likely to be in one class or the other. So mu, if it's true, then you're in this blue class. But if mu is false, then you're in this red class for the simulated data. And then we draw a binomial, so we add noise by saying that if you were previously in this latent class, the blue latent class, then you have some high probability, but not a probability of 1 of being blue in the end. And same with red, you have some high probability of being red, but not probability of 1. And so you end up getting a bit of noise here for this data set. Okay, so we constructed this, and you can imagine that a linear method, so if we use linear SVMs for this data set, you can imagine that it won't do well because this decision boundary that we require here is going to be nonlinear, right? So this is the sort of thing that, given what we've seen thus far, and if you didn't know the transformations that were used to construct this data, you would probably use k-nearest neighbors, because that's really the only nonlinear classification method we've seen so far. Okay, so let's so we're going to apply the linear SVM, and this is just a script right here. This is a script for visualizing the decision function for that SVM. So the decision function is a line, of course, because it's linear SVMs. And on one side we have its predicted blue, and on the other side it's predicted red, and it's going to do pretty poorly on a test set because on this upper side there's a lot of reds that are actually predicted blue, and vice versa, a lot of blues that are predicted reds down there. Okay, so let's look more closely at the RBF kernel. Let's apply the RBF kernel to this. And remember, the RBF kernel, it's going to predict your, you're going to get a prediction based on how similar you are, a given location is, to other data points, right? So you should look back at the notes and how predict works for the for kernel SVMs. But the basic idea is you fit those alpha parameters, right? And then if those alpha parameters, and then you look at the kernel between a point that you would like to predict and all of the data points, and then weight it by the alpha, and that gives you your output, right? Your decision function, which then is going to get thresholded just like in linear, SVMs. And so if you're more similar to points that are have a higher alpha, then you're more likely to be classified as a 1, right? And vice versa, right? And so if those points are neighbored by say a lot of 1s, then their alpha might be large, and then they're going to contribute more to the point. So let's see what kernel SVM with gamma equals 1 is. Remember, gamma equals 1. 1 is the lowest value we're going to use, and so a low value of gamma means a large value of sigma, means that the radius, that's the standard unit, is going to be quite large, right? And so we end up getting something that actually looks a lot better than linear SVMs, because at least it's splitting the space in a nonlinear fashion. But if you look back at the original decision, the desired decision function, this is a lot more smooth than we would like. And you can see there's a region, especially in here, where there's a lot of reds that are misclassified. So we're going to increase our gamma, and that's going to decrease the radius, which is the standard unit in the RBF kernel. And we get a more complicated, more sort of curvy decision function. And down here, there was a little bit of a region where there are a heightened number of blues, and those are still predicted as red. And so this radius might not be small enough, and so gamma might not be large enough. So let's increase gamma again and just see what happens. So here we get something more curvy, and then we get this blue region here. But something interesting that's starting to happen, this decision boundary seems to be overfitting in some places to data, right? So it's getting a little more jagged around here. And so we might start to overfit as we increase this gamma, right? So gamma sort of is taking the role of the reciprocal of k in k-nearest neighbors, right? The larger gamma gets, the more local become our decisions. Just like the lower k gets in k-nearest neighbors, the more local our decisions become. So let's increase gamma again and just see what starts to happen. We start to find these regions, these kind of spurious regions where we would like to predict, where it's predicting blue, where maybe we would like to predict red, and just increase gamma even further. We get something that's filled with sort of these very spurious regions where we're predicting as blues. So it's a bit I think the big challenge here with understanding this is why the kernel machines exactly have this behavior of predicting things locally, right? Of making these sort of local predictions as we increase this gamma, how the effect of the kernel, what the effect of the kernel is on our prediction and on fit. So suppose we had a kernel that only used very local, so it was only non-zero in a very small, tight region here. Then if you look at the fit method, then we're solving that, we're going to be solving an objective where alpha I is really connected to the alpha j's that are only within the local region, because that kernel matrix is non-zero for ij pairs that are very close to one another. And so you can imagine that only local decisions are going to impact the alpha. Now that's not exactly true because of the regularization parameter, but it's sort of morally true. Then when you go to predict, you can see that only very local, only points for which the kernel is non-zero are going to really impact the prediction. And so that's sort of how you can think about kernel SVMs. And just go back and look at the formulation and try to get some sense of why we're seeing this behavior, that as we increase gamma, which is decreasing our sigma in the RBF kernel, why that's going to give us this sort of behavior.